In this video, we're going to continue our illustration of how to eliminate the parameter from a vector value function and see how that might help us sketch the graph. Here we have x is equal to 3t minus 2. I'm going to leave out the as a function of time because we're actually going to be playing with that. And it's easier to do that without those extra symbols in the way. And our second equation is 4t minus 3. And this feels like it should be linear, and it probably will be in the relationship between x and y as well as x to t and y to t. But let's see what the details are. In particular, things like slope and intercept, can we get those out of the xy relationship? Since we're most familiar with y equals formulas, let's get rid of the xt relationship here and let that go into equation 2 afterwards. So for now, let's take our x and add 2 to it. And then we're going to divide through by 3. X plus 2 over 3 equals t. If we take that equation and we sub it into equation 2, then we're going to have y equals 4t minus 3, but we're going to replace that t with the relationship over here. A bit more room. X plus 2 over 3, that's t, and then minus 3. So this whole conglomeration here is our t value. Now that isn't super obvious, but we can see that the patterns of a straight line formula are arising here. We have 4/3, positive 4/3 x, then we have 8/3, and we have minus 3. And so if we summarize that, we're going to get 8/3 is almost 9/3, is almost 3, minus 3, we're going to end up with negative 1/3. And that we can read off because it's a form that we're familiar with. It has slope positive 4/3 and an x-intercept of negative 1/3 for y. And so we can quickly throw that together and get a curve that looks like 4/3. For every 3 we go over, we're going to go up 4. There we go. A little steeper than 1. There we are. And that would all be great if I put the intercept in the right spot. So just arrange that conveniently. And ta-da! We're going to call that intercept here negative 1/3. That's our x, that's our y. And again, we don't have a directionality, at least from this form. But if we go back to the original form up here, what we can see is that there's a number of different ways to do this. But I think here, looking at the x value, we can talk about increasing and decreasing relationships. As time increases here, then our x value increases as well. We see whatever t is, as t goes up, x is going to go up. That's going to happen all the time. And so we can add the directionality to this trajectory, which is the particle will be moving along this line from the bottom left towards the upper right. Let's take a look at a more challenging example next. We've seen something that looked like an ellipse earlier, and so it makes sense to kind of revisit that idea. Some students may not have seen this before, many of you have, but if you take a quick look at this formula, you see this x squared plus y squared equals 1 formulation. And remembering that x squared plus y squared equals 1 is the unit circle centered at the origin. Circle, pardon me. And with that unit circle, we can do a number of different adaptations. The first is we can change the right-hand side, and that gives us the radius of the circle. Here it happens to be 1 for the unit circle, radius 1, but if we wanted a radius of 2, we'd put 2 squared on the side here. This looks fairly simple. For some reason, putting things as a fraction often makes the formulas look more complicated. But if you just take a quick look at the relationship here, this x squared plus y squared equals r squared, being a circle centered at the origin with radius r, it can be converted by dividing through all the terms by r squared. And we get x squared over r squared plus y squared over r squared equals 1. And so that's completely equivalent to the more standard formula up here. This just happens to be nicer. No one likes dealing with fractions unless we have to. Well, now we have to, because if we have an ellipse, we have different radii. So if you imagine this formula here, how do we capture different radii? Well, we don't have to. If we want to change it to have different x and y radii, we simply use different values in the denominators here, where we have an x component or an x contributor to the overall circle ellipse formula and a y contributor. So x squared over a squared plus y squared over b squared equals 1 is going to give us an ellipse centered at the origin, and depends on the values, but this length here is going to be a, or this coordinate here is going to be a, and the coordinate in the y direction is going to be b, and the extents, of course, are going to be out to minus a and minus b in the x and y negative directions respectively as well, just like a circle would go to -1. So this is an alternative form of an ellipse, and what we want to do is just make sure that the vector value formula that we saw a little while ago that involved something like that also satisfies that ellipse formula. So remember, what we had for this example was x equals 4 cos t, and y is equal to -2 sine t. And when we did a quick sketch of that, we ended up finding out that the particle or the trajectory would start here, and this one went downwards and around like so. And what we'd like to do is confirm that that actually is an ellipse form. And what we are going to be able to do to achieve that is to try to turn our given vector valued function, this one here, into a form that matches this by eliminating the parameter. So that's going to be our next step. Now, it is definitely trickier to eliminate the parameter in this kind of context here, because we don't really want to solve for t. We're trying to get a relationship with both x and y in it that's going to work out a special way. So what we can do is square both sides of each equation, because we have a destination in mind rather than just trying to discover something new. What we can do is get x squared equals 16 cos squared t, and y squared equals positive 4 sine squared t by squaring both sides of both equations. Once we do that, what we can try to do is see how these ingredients could be made to look like the equation in the ellipse. So it's certainly easiest if we recognize if the form that we're aiming towards, which is x squared over a squared plus y squared over b squared equals 1. So what we can do with that is just take an example of x squared plus y squared and see what we get. Well, that would be 16 cos squared t plus 4 sine squared t. Realize, okay, well that's just a mix of trig functions with different coefficients. So this is experimentations. We just look at that value. We do realize, though, that if we just had cos squared plus sine squared, if we just had those as a goal, then what we could do is cos squared plus sine squared by themselves add up to 1. Well, how can we achieve that? What we're going to do is divide this term by 16 and this term by 4. You can't just go ahead and do that, so we have to make sure that our starting point also has that construction in it. So what we're going to do is look at that relationship instead. X squared over 16 plus y squared over 4. Again, this is inspired by the destination we know we have in mind. Cos squared t over 16, 4 sine squared t over 4. Well, that just adds up to cos squared t plus sine squared t, and that, through the trig identity, is just 1. And so what that tells us is that all points on u of t satisfy the ellipse formula, which is x squared over 16 plus y squared over 4 equals 1. And we know how to draw that ellipse. Once we have that formula, it's an ellipse with radius in the x direction of square root of 16, so 4, and square root of 4, which is 2, and we know it is now exactly an ellipse, rather than just something that might maybe kind of look like one because it has the cosine sines in it. Now we have the confirmation by limiting the parameter of exactly the shape we've constructed.